Finished with the definition. Did you do the homework in the break? So which?
That's a very silly question.
Yes.
What do you mean here?
There are no silly questions.
On the right tensor product here. You're defining category.
Oh, I'm sorry. I did something wrong there. So see, no silly questions. The problem with response stuff yet. The analog, it's saying that if I take identity, so if from X to Y, then I can either take the identity B from X to Y. So this sends F just to F. Or what I can do is I can take identity precomposed with, so this is identity on blank, and this is identity on X. So this sends F to F bring identity on X. And then here there should be an actual isomorphism. And similarly, we can also put the identity on the other side. But you're absolutely right, that was completely wrong. Okay, so the question that I had asked at the end is go back and check which examples that we've seen fit into this framework, and are they strict or not? So which examples did we have? Categories, functors, natural transformations. What's that? Is that a bicategory? Yes. Hands up.
Which one was bicategory?
Categories, functors, natural transformations. Is that a bicategory? Yes or no? Yes. Hands up. No. Hands up. Is it strict? Is it no? Yeah, it is a strict category. So the point with categories, the functors, natural transformations, is that if you compose functors, then we really do get equality, right? Composition of functors is actually associative. You don't need any green stuff. What was another example of a bicategory? Think back of our examples. Bordisms. Great. Thank you. Bordism. So there are two versions. So I can either take closed manifolds, bordisms, diffeomorphisms, or I could take bordisms of bordisms, bordisms, and closed manifolds. And then I have to do the subtlety of up to blah, 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 this red star thingy. Both of them are bicategories. Both of them are not strict. Okay. Another example.
Even if you quotient out by these isotropies, are they still not strict?
I have to think about that, which I won't be able to do at the moment. But there are ways of making it strict.
Right. Okay.
So, I mean, bicategories, you can always strictify. Every bicategory is equivalent to a strict two category. So here we're still in game. Like, I mean, even if you don't care about this higher stuff, we can always strictify. Outlook, which we were discussing before after class. As soon as you go higher than 2, that will not be true at all. Okay, so there you really have to work with non-strict things. The last example we had was this algebras, bimodulus, homomorphisms. That's also a bicategory, but not a strict. Okay, what about 3 categories now? So good luck. Please try to figure out what a 3 category is. So it's easy to give one definition, namely for strict. Just repeat this, add 1 extra layer, and you're in business. But if you want to do the analog of this non-strict stuff, I mean, these associators, I mean, in unitors you have to have pentagons and triangles now, not relations, but actual extra data. So just as before, when we went from 1 to 2, the associator was new data that appeared. That used to be a condition, and now it's new data. So just like that, for 3 categories, the pentagon becomes stuff you have to add. And then you get all sorts of new diagrams. So yay, we can check a lot of things. And nobody ever wants to do that. We were saying before, like the definition, I think is 16 pages long. So maybe not, I mean, you can do things partially. And I mean, like, I really admire people who can, because I just get confused. I can't.
Claudia, slight comment. I confused it with 4 categories. That's
4 categories is 16 pages. 3 categories is 3. Okay. Still enough. Right. So we will encounter examples tomorrow, actually. All right. So I wanted to kind of motivate for you. Some of you might have been at last year's school and conference. So David Ayala in the conference made this very beautiful picture here, explaining that if you want to go, you know, from 0 categories to 1 categories, fine. Then to 2 categories, you know, there might be some waves, but I mean, you can still do something. So the set way, this is what we've been doing, is like crawling along the ocean floor. And then doing like infinity stuff, which we'll see later, is like taking a sailboat. And then, like, if you want to go from 2 to 3, you know, like you can still do the set way. There will be ditches along the way, and it will be hard, and then you will have to climb higher, but you will manage. For 4, you already have singularities appear. So I love this cartoon. This is great. And you know, you would like to go to 4, 5, and there's a physicist flying on top of it. That was amazing. So in the school, other David, Jordan. So this was David Ayala. David Jordan in the school modified this and made a huge animation, but I couldn't reproduce it. But basically, upshot was you have these mountains. And then in the hot air balloon up there, there were David Ayala and John Francis flying. But what I want to kind of, you know, the point I want to make maybe is that I don't want to go from mountain to mountain. I want to do it all at once. Okay, so we'll kind of do this. We'll zoom out. We have Earth. You know, we have a mountainous mountain range, and you know, some might be 1 high, some might be 2 high, some might be 4 high. But we would like to have a version of, you know, not doing each step individually, but being able to attack all mountains at once in some sense. So that's my philosophy. And these infinity n categories that, I mean, I'm not sure I will actually be able to tell you for all n at once, but at least give you a glimpse of how to do that. And maybe, you know, you first have to build a spaceship. You first have to go all the way out and fly to space. But once you've done that initial technical setup, then you don't have to kind of do each mountain individually, but you can do them all at once. At least for definition, you know, like that. But I really want to stress that if you've mastered the technical framework, there's no difference in difficulty of doing 2 or doing 16. That's somehow the point I wanted to make by this drawing. All right, I'm not claiming I have a spaceship. I'm building one. We're trying to build bits and pieces of one. All right. Any questions before we try to build a mini spaceship? And obviously, I'm not as good at drawing as those other people. So yeah. Hopefully, the spaceship won't be broken. You know, the problem of the spaceship is then you don't see the details anymore sometimes. So I'm not saying that this is the better approach. It's just a different approach, right? All right, again, what is a higher category? So higher category now in this lecture will mean infinity 1 category. So the full more details. So let's revisit categories. And so the first goal will be to reformulate the definition of a category. We'll first reformulate the definition into a category into a way that you can do something like higher with it. So maybe a disclaimer here. If you try to go and look up what an infinity one category is, you will find many different definitions. And there is a precise way in which they're all equivalent, which I don't want to dwell on in these lectures. There's a precise way in which these are equivalent, and the most common model is not the one that I will tell you about. Most common is that of Scheimbauer quasi-categories. And this is what Lurie calls infinity category. Okay, just to give you a disclaimer that you might see now something slightly different. But for the purposes of seeing all mountains at once, another one is a little bit preferable. Also there are many different choices, and it's just that for the purposes of our applications, this one is useful. All right, so first, again, just a disclaimer, this will be a little technical now. If you get lost, don't give up. We will rope you back in. So we look at delta. This is the category of linearly ordered finite sets. And to be fully precise, usually we take a skeleton of that thing. If you don't know what that means, just ignore it. But what are our linearly ordered finite sets? Well, we have objects, one for each cardinality. So we have something called 0, we have something called 1, we have something called 2, and so on. And so in N, this is supposed to be a linearly ordered finite set. So I have N objects, N plus 1 object, sorry. And it's supposed to be linearly ordered, so I just put the linear order on. And then I have to tell you it should be a category, so I have to tell you which morphisms. And order preserving, not strictly. So they're monotone, not strictly monotone. Thanks. So I'll give you morphisms. Examples are 1 to 2. We have 3 maps. We have more than 3 maps. We have greater maps. I want to write down 3 maps. That's what I wanted to say. We have 0 goes to 0. 1 goes to 1. We have 0 goes to 0. 1 goes to 2. Or we have 0 goes to 1. 1 goes to 2. Okay. We also have 0 goes to 0, 1 goes to 0, and the same for 1 and 2. And those now I think are all 6 maps.
Three injective maps. Three injective maps.
Yes. Exactly. You'll see in a moment why I made the mistake, but. All right, from 2 to 1, we have 4 maps. Here I was more careful. So I have to tell you where 0, 1, and 2 land. So 0 goes to 0, 1 goes to 1, 2 goes to 1. Maybe I was not careful. There's also the identity. No.
Yeah.
Oh my God. Thank you. This is being recorded. Oh. So we have 0 goes to 0, 1 goes to 1, 2 goes to 1.
One goes to 0 probably.
What else can we do? We can send everything to 0. We can send everything to 1. All right, so graphically, we can depict our category as follows. So we have certain maps which go from left to right. And we have certain maps which go the other way. And then composites of those. So the essential ones I wrote down were these 3 green ones. And the 2 I forgot were composites with these. Okay, so definition. A simplicial set is a functor from delta but up to set. And we denote this by x bullet. And the bullet is like n goes to xn. And what I will want to do very soon is I want to replace set, for instance, by space. And then I just write delta up to space. So now here I have an example. Let's see BA, and I mean, we need a small category. If you don't know about these differences and don't care, don't worry. The nerve of C is NC, goes from delta up to set, and sends 0 to the objects of C, 1 to the morphisms of C. It's actually better. Two to the product of the morphisms of C cross the morphisms of C. And so on. So n goes to morphisms of C times N. Now I have to tell you what to do with these maps. So from a morphism, I can extract its source and I can extract its target. From two morphisms, now I can do three things. I can project onto this, to the either component. So it's just remembering this or just remembering that. Or in the middle, I can compose. And then all of the other maps are combinations of these, or just projections or compositions. Oh, thank you. So I did, yeah. From my notes, I changed up the board and I should not have. Thank you very much. You're absolutely right. How it works, right? Okay, so maybe this is a good point. Graham was saying, what did I do wrong? I should have taken composable morphisms. So what I want to do is I can fix this formula, namely by writing the fiber product over objects where this map here is the target and this map here. So this is maybe a very good preview actually for what's to come. So Graham's a local expert here because this ultimately goes back to him. And there are very special maps here. Maybe I'll put this here. There are special maps in delta from 1 to n, which sends 0 to I and 1 to I plus 1. So this is for every I from 0 to n minus 1, I have such a map. And these induce maps going from xn to x1. I'll call these gamma I. So in my case here, something in here looks like a finite list f1 to fn. Each fi is a morphism from xi to xi plus 1. And what do those special maps do? It just extracts fi. That's what you should remember. Maybe this x, yes?
Here it's different than it's not the objects, it's the image of the neuron.
Here it is, yes. Here, this is general. This is any simplicial set. And here you see these are exactly composable morphisms, right? The target of f1, which is x1, is the source of f2. 0 x1 x2. And so reformulation. Well, I could have also formulated as a theorem, but I want to just be provocative and say this is actually my now definition of category. And if you wish, small category, but I don't want to go into the details, is the following. A category
It's every Thursday, 11:30.
I'll just write. Category is a simplicial set X such that so from Xn I have these maps down to X1 and I can actually assemble them. So I have n of those. So I land in the product, but similarly to Graham's comment, we shouldn't be looking at the product, but rather as a fiber product. Actually, here I can put my x zeros. So this is due to the fact that if you look here, the image of the ith one, the source of the ith one is the value at 0 of the ith one is the value at 1 of the I minus first. So they fit together. And the condition is, I'll just put a sign here. This is a bijection. I'm lecturing in German this semester for the first time in a long time. And so now I'm constantly going back between English and German spelling. It's horrible. And now if you add actually a monoid, we can define is a category in the sense with x0 is just a point. So this is maybe a motivation where this comes from, reformulating what monoids are. But the advantage of this definition over the classical category definition is we can iterate this. One thing I did not tell you before, which is maybe an aside for those of you who know what that it means. If you look at the definition of two category, it's actually what we could say is a category enriched in categories. Enriched means that the HOMs now are not a set anymore, but now, or collection, but rather themselves again a category or like an object in. And so similarly here, we can try to start iterating. So we say a category object in some other category S with a Cartesian product. This is a simplicial object in S. So that's just replacing that I put set here by, I put S here. Such that, and now I put the same condition as I did above. So this condition is called the Siegel condition. I'm sorry I have to mention your name so many times. And let's take some examples. Comments, questions, confusions?
I was wondering what SX or zeta X.
S is some category and product.
So,
X
oh, it's
is
okay. It's a
different
monoid.
product. It's a monoidal category, yes. But not any monoidal, it really has to have a Cartesian product.
That some condition on Cartesian product is a limiter code.
Cartesian product is just the product in the sense of category theory. Yes?
How do you know that the fiber product exists?
A priori we don't, thank you. With finite limits, finite products. Cartesian product, and and these exist. Finite limits, sorry, and finite limits exist. Very good point. I mean, I'll modify this in a second, even more so. All right, so example 1. Just take S with the product to be categories with a product. Okay, and so what we get is strict categories. So how do I get bicategories? So I'm on purpose here just made a symbol like this. So if I have a notion of weak equivalence, if I have a notion of weak equivalence, so this is now equivalence of categories, then I can write this down as just weak equivalence, not isomorphism. And to be fully precise, I have to modify a little bit here as well. So now this will be actually an infinity 1 category with Cartesian products, etc. Now this definition looks circular. Okay, I define it. I will want to write an infinity category. An infinity 1 category is this. But I can assure you, one can make this non-circular. But the point is that here we want the notion of weak equivalence. And usually in this setting, it is understood that we take the correct notion of homotopy, of fiber product. So we will not write that. Okay, so this is maybe a point of confusion for some of you. Feel free to ask about this, but I don't want to go into too technical details. I want you to remember this here, and that this here we're actually treating S as an infinity category, which means that we only want weak equivalence there and not isomorphism. So my example 2 is we can just take cat n-1. If these are possibly strict n-1 cats, assume we already have defined them, then we get strict n cats. Okay, and then we can try to weaken.
So no matter like take cat n-1 to be the strict or the weak definition, you'll always get the definition of strict n categories.
No. I mean, if we it will be partially strict, right?
Yeah.
The new stuff that we
No,
get will be strict, but the old stuff will be weak.
Yeah, but at every step you have to do your weakening.
Yes, exactly. And so let's try to get fully weaken and add this like infinity stuff. is now we take S together, the product being category of spaces with the product. But as before, what we actually have to do is we have to treat this as a weak thing. So we have to use weak equivalences. Weak homotopy equivalences. So what we're really taking here is this is the infinity one category of spaces. And for the experts amongst you, these are just infinity groupoids. This, I want to get somewhere with this and get to actual n categories. I don't want to talk too much about that, but if somebody has questions about this, I'm happy to tell you about this. The fact that we can use these spaces as infinity groupoids is called the homotopy hypothesis, and that would be another lecture, I guess. But so here, I mean, in this setting, what we really write is here we have a space, here we have a space, here we have a space, here we have a homotopy fallback, and we can actually write this down. So, I mean, in applications, space really means topological space. Since this is not, I mean, we're just writing down a bunch of spaces, a bunch of maps. Where are they? Here. A bunch of these maps going between the spaces. And then we have to check one condition. Hopefully that's not as scary as maybe first it sounds. Like we have to write this whole layer and many compositions and many directions, and we have to check axioms, etc. Just have to write down a bunch of spaces, and we have one condition. Plus these simplicial maps here. Where are they? Plus these maps. Plus then check this one condition.
This setup, do you always only naturally get the infinity one category of infinity n categories and not the infinity n plus one category?
Yes.
Can you fix this in this setup, or do you need to use a different model?
No, I mean, here you really, I mean, you have access to the higher morphisms, but not just from this iteration procedure. So basically what you're doing here, if you wish, is I can say, where's the category object definition? Is it gone? Yeah, that's gone. So I said category object in S. So if I call that cat of S, then I can do cat of cat of cat of cat. And if I start with cat being infinity cats, then I get, but it's always an infinity one category this way. You have access to higher morphisms, but then you have to do something clever. So basically you use that, say a natural transformation is, a natural transformation from C to D is the same as a functor from C cross 1 to D. Something like this. Any other questions? Okay. I can now give a definition. So the advantage of this setup is also that this is very, I mean, it's really written in the language of categories. Really, as long as I kind of put something useful in here, I mean, this being a, I mean, I was kind of hinting at it, this being a actual category or this being an infinity one category, something that really doesn't make that much of a difference. We can always write this setup. That's somehow the advantage. So maybe an aside. Yeah. So definition. This is due to Charles Rusk. Siegel space. Or nowadays, sometimes this is called pre-infinity one category. Or flagged infinity one category is simplicial space X from delta op to space. And now, so this here is the infinity 1 category of spaces with the Cartesian product as a monoidal product, such that xn going to x1 over x0 and so on is the weak equivalence. And maybe as an aside for the experts, so going back to a question before, this is actually more of like a double category where in one direction you have a groupoid and one direction you have a category. So usually you have to add a equivalence axiom to make this an actual 2 category. So sorry, 2,1 category, but if you have no idea what I'm talking about, just ignore it. So an infinity 1 category, so I'm just implementing what I just said. Infinity 1 category is a flagged infinity 1 category such that a univalence, and for Siegel spaces is usually called completeness, axiom satisfied. I don't want to spell, I'll just write something here, and if you don't know what this means, then just ignore it. Yep.
Are we doing the weak version here?
Yes, that's why I wrote here, this is an infinity 1 category. So I just want to kind of get you, to see the notation. I'm not writing down the H here because if I write infinity 1 category here, it doesn't make sense to talk about H. So I just want to, I just want to kind of push away all these technical.
Sorry, why do you have to take delta op there in these definitions?
Delta up?
Yeah.
It's just the structure that we saw here. The structure that we see here is that if we go from 1 to 0, we have source and target in this direction, not in the other way.
Right, okay.
Every question. So somehow, probably should have stressed this at the end of the last lecture, at the beginning of this lecture. Everything we're doing here is developing a language. We just want the language to capture what we see in our examples. For me, to be, there are people who do infinity categories or higher categories for themselves. I don't. I want them to be, a structure that organizes what we see. Okay, so most higher categories are actually these flag types of things. That's something I already said before. So, okay, so if you got lost, now is the point when you maybe can come back in, because now we're going to go back to Bordisms. I thought I would have more time, but I have much more time tomorrow. So it's fine. But we'll give a first indication of how Bordism form such a thing.
Claudia,
Yes.
one question. This, I must miss something. What is the difference between the definition of a Siegel space and your example 3, where it is?
They're the same.
Okay, okay, great. Yes. Okay.
That's exactly what it is. I just wanted to have it as an actual definition an infinity 1 category is. But probably I should erase. Oh, maybe I don't want to erase this. Are you done writing? Is it okay if I erase this?
I am. I can't speak for all.
I'm done writing.
2 out of.
I'm writing. It's my
Own fault, who is not done right. Well, now it's too late. All right, Bordisms. Okay, so. So this will be n comma 1. I should be doing this, but I'll just abbreviate it to be x because I don't want to write out board and well, I should write d comma 1. d comma 1. So d is our dimension. And so the idea what is xn? If you look over here, what was xn? Xn was supposed to be composable morphisms, right? Exactly what Graham pointed out, these are supposed to be composable morphisms. So what are composable Bordisms? I want to change my point of view slightly. So xn are composable Bordisms. And now I want to change my point of view. And I think this is natural with how we motivated the Bordism category. How did we motivate the Bordism category? We said we take some large manifold and we want to be able to chop it into pieces. And I want to reconstruct the big thing from the small pieces. So we weren't actually gluing Bordisms together. We weren't gluing manifolds together. We were taking something big and chopping it up into little pieces, right? So this is the point of view that I want to say. I take a big Bordism or manifold and for which I know how to cut it into pieces. So let's draw a picture. Might be something separate floating around, I don't know. Yes. And so what can I do with this Bordism? I know I can chop it up into pieces. For instance, here or here. Here. So here I have 1, 2, 3, 4, 5 guys. So this should be a picture in X5. So technically what I will do is, as before, we will add our timeline. And now I will add regions where I'm allowed to cut. Yeah, let me do that. Right, so now I gave you the xn's, at least pictorially. So the number of cuts is exactly n minus 1. Here I have 4 cuts, so I'm in X5.
You could cut the figure as much as you want.
Yes. And then I'm just in a different X. But in a category, I can do that. I can compose like arbitrarily long strings as long as they're finite.
But not every cut is allowed, right?
Not every cut is allowed. Right? So where am I not allowed to cut? I'm not allowed to cut, for instance, I mean, it's a little hard to see in the picture, but somewhere here, where, I mean, I drew in what the picture would be, right? The picture here would be a figure 8. Right? This is not a smooth manifold. So can't cut here. If you cut here, you get a circle. If here, you get 4 circles. Here, like these are all fine. But there are some points, namely exactly at these Morse points, where I'm not allowed to cut.
But for 2, it's 4 circles right now. I couldn't take out any of these circles.
Here?
Yeah.
No, I would have to kind of erase a whole component of the board. Okay, so let me get more and more precise. So let xn be, and remember I want to see space. I want some space, and I won't dwell on this now. This maybe tomorrow, but probably we'll just ignore it. Of the following things. So M is a d-dimensional submanifold of, so I drew this suggestively because I will take an interval here. So I choose elements A, B, and R. And then M should be a submanifold of the open interval A cross B. And I mean, I'm drawing, which means I'm implicitly embedding it somewhere. Just put some very large R. I mean, one could have also chosen to say what this is it's a manifold with boundary. And then there are in topology theorems that tell you that you can always embed it in this way. But the choice of embedding, I mean, first of all, this is exactly how we picture these things. And second of all, it actually helps to get the space. Okay, so I have my AB, I have my submanifold of something, and now I have to tell you where to cut. I had drawn these purple. Oh, that's not a good color coding. Yellow here. Now I have to add the data of where I'm allowed to cut. And so there are various choices of how one can do this. I'll just write down one of them for you. We're going to choose closed subintervals. I0 to IM of this AB. With endpoints A0, B0, A0 equals A, up to AN, BN, and BN equals B. Let me draw this in. Maybe I'll erase this first one just because I don't have enough space. I'll make this one really close here. So let me start here. So at the bottom here, I have some interval. This is an interval. This is an interval. This is an interval. And then here I actually have 2 intervals. And then maybe I have one here. And then I have one at the end. Okay, I could have chosen these intervals to just be single points. There are some application reasons why in some applications it's more useful to have intervals rather than points. Right. And now we have to formalize conditions on these. So for the intervals, we want that the left endpoints are ordered and the right endpoints are ordered. What else do we want? We have a closed submanifold, d-dimensional. Right, I want, so if I can now compose this just with a projection down to AB. Let me call this pi. And then I have pi is submersive, i.e. a local diffeomorphism. Wrong dimension. It's submersive over the intervals. So this subversivity condition means that if I choose any point in here, then my pre-image will actually be a manifold. So if I choose a point here, let me make these green. I'm missing green, yeah. If I choose points here, then I get exactly these pre-images here. And it tells me the submersivity condition is exactly what tells me that I can't do this red thing. Let me think, did I forget something? That's fine. Yes.
Sorry, I just want to make sure I understand. So the purpose of this interval AB is so that we can keep the boundary of M at points A and B.
Yeah.
So we want this to be a closed interval, AB?
No, it's actually open. The point is that if I go to higher dimensions, I did not want to have to deal with the theory of smooth manifold with corners.
Okay.
Okay, so I mean, in this setting, we could have chosen closed and then we just have manifolds with boundaries and everything is well behaved. It's just that when we were constructing the gory details of this stuff, like I was terrified of manifolds with corners and dealing with smoothness at corners, etc. And so we avoided having to do manifolds with boundary because now they're actually just manifolds. Yes.
So what stops your what here disallows your manifold from going off to infinity near A and B?
Doesn't. I don't care. So the philosophical point is that as soon, right, thank you. That was a condition that's missing. I is proper. Thank you. I knew I was missing something. Okay, so the point is that like I want to actually think of my Bordism as being like the part that if I choose a point in that interval, a point in that interval, I take the pre-image of the closed thing. That will actually be compact because of the properness. So I don't care if at the very end it goes off to infinity, because as soon as I'm a tiny little bit away from the endpoint, it will be compact. Any other questions?
Related, but what is the source of this word?
What do you mean by source?
Yeah.
So,
I think so. I think
so this is an X5. Okay, so this is an X5. So you should think of this as a string F1, F2, F3, F4, F5, morally speaking. What do you mean by source of such a composable string?
yeah, I guess it should be the source of the first thing, right? So it's somehow maybe
Okay, if that's what you mean, yeah. So if this is like X0, F1, X2, F2 ones, and if you mean this one, okay. Right, so what's something in X0? I mean, I'm out of time. I wanted to kind of maybe postpone that until tomorrow, but if it's okay, I'll continue. I think we have a longer break now because lunch is only at 1.
You have 2 minutes because we started late.
Oh, even better. So if you look at what happens for x0, for x0, I still have the definition d-dimensional submanifold blah, blah. It's supposed to be an object. I actually want in Bordism's x0 to be d-1 dimensional. But we have a condition that it's everywhere submersive. This is worth writing out in the 1.5 minutes. This is at least over compact. It's a trivial bundle. So this is just some M0 cross AB. At least if I go to something smaller. And so M0 is what you think of as the object. And that's the fiber over any point. Okay, so the thing you think of as a source is you take any point in here and you take the fiber over that. And that's what you think of as the source of the Bordism in the classical sense. Oh, sorry. Yes. So this ties into saying like we had to add collars to the data of Bordisms. So my philosophy actually, I mean, I know this is a little bit controversial, but my philosophy is Bordism category should not have objects d-1 dimensional things. It should really have d-dimensional things, but which are little cylinders on a d-1 dimensional thing. And this here implements this in a very nice way because here my object is actually the preimage of the whole purple thing. So this is my whole source. So it's actually naturally, it looks like a little collar. Well, that's the philosophy behind it. But it's really useful actually once you start thinking about geometric structures to think about it this way. Okay, I have not told you, I just told you what xn is. To get a Siegel space, here we also need to have maps between these xn's. So maybe I'll let you figure that out yourself. Feel free to ask. And then I'm taking requests if you want me to continue with this example tomorrow and do that in a more detail, or if we should go over straight away to the algebras.